Hey everybody, my name's Sam, and today we're going to talk about how researchers predict meteorological events that cause a period of low renewable production, both solar and wind. And later in the presentation, we're going to talk about how high energy demand may be impacted by this. So these meteorological events are most commonly conferred to as anticyclonic gloom. But in the paper we're going to discuss are called Dunkelflaute, which in German means dark lull. So as we said before, Dunkelflaute is a combination of two German words. One means dark sky, and the other means calm winds. Put the little Zen Buddha in there. It primarily happens in the winter in Europe. It's characterized by a high pressure system. And it's kind of weird that the other characteristic is that it has extensive cloud cover, because that doesn't usually happen in a high pressure system, but we'll talk about that. There's a strong inversion layer. The wind's really calm, and the surface temperature is also really calm, and it can be pretty foggy, and we'll talk about that too. And I included the little book of Hygge because it basically talks about how in the Scandinavian lifestyle or Danish lifestyle, during the winter, during cloudy events and winter, in the winter, I already said that, they boil tea, they heat their house a lot, they get really cozy, and this can be a high demand scenario that is affected by this low energy production scenario. So when I saw high pressure, I'm like, okay, let's figure out what is causing this Dunkelflaute. Is it a high pressure system? And yes, it is. But there are actually 4 types. The first one is called the thermal anticyclone, and they occur during the winter months in the Northern Hemisphere. And they're a lot more common in like Canada and Russia and huge continental land masses that get really, really cold because as the surface gets cold, it basically will cool the surrounding air, and it causes this high pressure system to develop. The type of anticyclone that is a Dunkelflaute, I believe, is a convergence anticyclone. And that's basically when the jet stream starts to meander quite a bit, and as in the bottom left graphic, and basically it creates these troughs of low pressure and high pressure, as we'll talk about in the next slide. And the next type of anticyclone is called a blocking anticyclone. And that's basically when the trough will split and it creates this bubble of high pressure that the jet stream cannot penetrate, and it sort of just moves around it, which is not a Dunkelflaute anticyclone. And then the last one we'll talk about at the end of the lecture is a subtropical extension cyclone, and it's when in the Northern Hemisphere during the summer, this high pressure belt near the equator starts to stretch, and it starts to encompass Southern Europe and the British Isles. And that's not a huge problem right now, but it could become a bigger problem in the future and lead to more of these low renewable generation scenarios. Okay, so in 2020, these researchers wanted to basically see if they could use WRF to model one of these Dunkelflaute events. And so they decided to look at one off the coast of Belgium, and I think on mainland Belgium as well. And this event lasted 9 days in 2017 during the winter. At the same time, some Belgian power plants malfunctioned, which lead to a drop in generation. It was very cold, so people were heating their homes again. In the bottom right image, I included a list of power plant outages in Belgium. And yeah, there's quite a few of them. So it's that part of it is a constant phenomenon. So I thought that was kind of interesting. And currently Belgium only has 3 operational wind farms, and they're right next to each other. So I talk about low correlation, huh? So yeah, some other parts of the study is offshore, the temporal granularity was a little bit less fine than the onshore measurements. It's a disclaimer. And what really confused me was why there were overcast cloudy conditions in a high pressure system. Like I had never heard of that before. And after some research, I found that this is happening because of the NAO, the North Atlantic Oscillation. And it looks like that chart we had on the last slide in the negative mode. When the jet stream starts to meander a little bit. And during the negative mode of the NAO, all this warm air from the Azores and sort of subtropical Atlantic is being pushed up into the North Sea region, and the anticyclone is sucking all this moist, cloudy air down into itself towards the surface, and it's making this cloudy fog layer over the North Sea. So I thought that was super interesting, and it's very, very geography dependent and very specific to this area. I'm sure there's other examples, but we don't have like a lot of wind farms or solar there. So I'm sure this problem is going to come up again in other countries. All right, so let's look at some of the results of this study. They ran this WRF simulation for 2 weeks and found that it was not very accurate after 4 days of initial conditions and initial parameters were input. And if you look at the top right series of graphs, it's showing wind speed at different altitudes and then at different sites, observed and WRF. And I think the bottom uses 2 different reanalysis data sets, ERA5 and ERA interim. And yeah, they got off at around day 20 or the 21st of January. And they were not very accurate, let's say. If you look at the bottom right series of graphs, that's sort of a throwback to our atmospheric boundary layer lecture and looking at the vertical profile of the wind and potential temperature. And as the graphs go towards the right, that's basically chronological. First 2 are on the 15th of January, second 2 are on the 25th, or sorry, the 24th. And you can also see that the WRF gets pretty off from the observed data after about a week. So this made me think, that's about it for the study, but this made me think in areas like the North Sea, where the topography doesn't change a whole lot across country borders, does low correlation and a large transmission grid really matter if it all looks like that cloudy picture right there during this Dunkelflaute event? So yeah, so let's talk about Dunkelflaute in the US just really quickly. Is it common? No, not really. The US is a continental landmass with varying topography. So these huge high pressure systems aren't super common. And if there is a high pressure system in a small part of the country, then basically the area can buy electricity from another area within the country and have it transported through the transmission grid. So it's a lot cheaper than having to import from another country, like in Europe. And one thing about solar resource prediction in the US is pyroheliometers used for predicting solar wind resource have kind of fallen out of style. They're not super useful anymore because we can basically just use satellite reanalysis data with WRF solar to get really accurate predictions. So let's talk about load for a little bit. Especially in the US, there's only one Dunkelflaute event with a high energy demand as well. And that was recently in 2021 with a Texas freeze when the plants shut down, but there's also a huge energy demand because everyone was cold and needed heating. But so far that's the only one that I could really find. But another high demand scenario that piqued my interest was the Super Bowl. And this was because basically on Super Bowl Sunday in February, energy peaks in the US up to around 105,000 megawatts in this study that I found on the bottom left. And this is quite a bit more than the typical winter load. So if there is a Dunkelflaute in an area of the US during Super Bowl, then that could lead to some transmission and distribution problems for sure. But there haven't really been any studies into the two. So lastly, I just wanted to bring up how these Dunkelflaute scenarios might increase in Europe with climate change. So as temperatures are becoming more homogenized latitudinally, the Hadley cell close to the equator, right by the intertropical convergence zone, is going to start to migrate northward mainly. And it also migrates southward, but not as high of a rate. And this could lead to a lot more high pressure activity closer to mainland Europe. And this could lead to more Dunkelflautes and is something that the renewable industry should be looking out for. And yeah, that's basically my presentation. Thank you guys for listening. And those are the scientific points that I tried to touch on. And yeah, thank you.